presentation and for the introduction. As you said, I'm going to present here a project that I've developed with my PhD advisor, Assir Abdul, my colleague from EPFL, Andrea Zanoni, who is as well a doctoral student in the chair of Assir, and with Grigorios Pavliotis from Imperial College and Andrew Stewart from Caltech. So I'm going to talk about an alternative to subsampling for drift estimation of multiscale diffusions, which is given by filtering the data. So let's start with some motivation. So multiscale diffusions are an appropriate model in different fields of physical and social sciences. In particular, there are some applications in oceanography and atmospheric science, in econometrics, when modeling markets with the micro-macro structures, and for chemical reaction which happen on different timescales. So all these phenomena are very complex, and even their mathematical model are extremely complex and present different timescales. So due to the different timescales, the numerical, for example, the numerical approximation of the solution to these mathematical models can be overly expensive computationally. Therefore, it is a possible goal to determine effective models which capture the slow variation, disregarding or taking into account the fast variation of the problem, to create an effective problem which is capturing the slow variations of the multiscale problem. So if the data of the problem is given, so let's say the functions or of your model are given, then you can use the theory of homogenization in some instances to compute the effective model. Otherwise, what you have to do is to rely on inference techniques. And therefore, where you are given data from a multiscale phenomenon, what you may wish to do is to infer from the data an effective simple model that captures the slow variations of your phenomenon. So since the multiscale model where data comes from is actually multiscale, so it comes from a complex phenomenon, and you're trying to infer a simple model, you're confronted with an issue of model misspecification. In order to tackle this issue of model misspecification, it has been shown during the early 2000s that it's necessary to pre-process in some way the data. So this pre-processing is oftentimes done through subsampling the data. So you have data that comes at a very high frequency, which is comparable to the fast scale of the process. And you need to subsample the data, so take just a subset of the data, and do your inference procedure over this reduced set of data. This subsampling is widely employed and has proved to be very effective in lots of scenarios, but there are some downsides of it. First of all, most of the times you need to know the scale separation. So you need to know how faster is the fast dynamics with respect to the slow dynamics, which is something you don't always know. So second issue is that the results of your inference procedure are most of the time strongly dependent on the rate at which you subsample. So there is a wide range of, a range of rates for which the results theoretically are asymptotically good, but in finite computations, you don't know which would be the optimal subsampling rate. And the third, and maybe the most important issue, is that by subsampling, you're actually throwing away a lot of data. So in, let's say, nowadays, more and more mathematical applications and physical applications require a lot of data. And throwing some of them, or actually in many cases, most of them away, seems not to be a very good idea. So what is desired for a possible new method? So the first desired thing is that the result of the inference procedure are consistent with respect to homogenization theory. So in case the data of the problem are given, then through the theory of homogenization, we can compute an effective model. So we would like that our inferred simple model is consistent in this case with the theory of homogenization. The second thing that we would like to have is that if we introduce some parameter in the model, let's say in the method, we would like that our results are consistent, robust with respect to this parameter, as it is not the case in subsampling, as I said before. Then the third desideratum of the method is that it's applicable as a black box tool, meaning that the knowledge of scale separation is not required in order to perform the inference procedure. And the fourth desideratum is that the method is amenable to the Bayesian framework. So inferring the parameter in a Bayesian way allows to have a full uncertainty quantification over the result, since you don't have just a point as the result of your inference procedure, but you have a whole posterior measure, so you have much more information, for example, concerning the variance of your estimator. So let's see which model is we are interested in. So we are interested in this multiscale SD of the overdamped Langevin kind, where we actually, for simplicity, we talk here only about the one-dimensional SDE. So X is a one-dimensional diffusion process, which solves this differential equation where we have a slow scale potential. The first term is a slow scale potential, which is actually a vector valued function. So we have here capital N functions, which are multiplied by capital N drift coefficients. And this is the slow part of the potential. Then we have a fast part of the potential, which is we consider to be periodic. So we have a fast potential, which is smooth and periodic with some period L, multiplied by 1 over epsilon, over where epsilon is the scale separation parameter. And then we have an additive source of noise. We have here a standard Brownian motion, and sigma is our diffusion coefficient, which we take by square root of 2 sigma for normalization purposes. So graphically, we have that this model describes the motion or in a potential of this sort. So here we just take capital N equals 1. So we have just one slow potential, which is quadratic. Then we take alpha equals to 1. P of y is just a sinusoidal function, and we take epsilon to be 0.05. And we have here in black dashed the slow scale potential, and the gray line is the multiscale potential. So what happens? The diffusion process moves in this potential. So it will eventually go to the bottom here, to the minimum of the potential, but it stays stuck in this local minima. And it can escape this local minima only because there is a diffusion term. So what happens here is that we are slowly drifting towards the minimum, and then we get stuck in this local minima and jump out of them as soon as the diffusion kicks in enough. So clearly, the motion in this gray potential is much slower than the motion in the slow scale potential. And it gets closer and closer to the speed there will be if there were no fast component, if the diffusion coefficient is bigger. So as a further remark, let us remark that our framework is a semi-parametric one. Indeed, we have that our slow scale potential can be written as, of course, as the sum over I of alpha I vi, if we choose vi to be the basis of some appropriate function space, then we have that if we are inferring the coefficient alpha, the drift coefficient, then what we are inferring is actually approximately a function. Actually, it is a function in appropriate function space. If we would let n to go to infinity, then we would be in a non-parametric framework, and what we would be doing inference on would be properly a function. So let's just quickly recall, for those of you who are not completely familiar with this homogenization theory for this kind of problems. So we have that there exists indeed a simpler model where we don't have the fast scale potential, so it's just a slow scale potential. And we have that xt epsilon, the solution we had before, converges to xt in law when epsilon goes to 0. And we have that the drift and the diffusion coefficients are actually multiples of the original drift and diffusion coefficients, where the proportionality constant k is given by the average with respect to this measure, which is actually the invariant measure of the fast component of our process. And it's the average of this quantity 1 plus phi prime squared, where phi is the solution to this boundary variable problem, which is taken with periodic boundary conditions. So analytically, one can show that this coefficient k lays between 0 and 1, and in particular that k goes to 1 if the diffusion goes to infinity. So let's see graphically what this means. So we have the same picture as before. We have the slow scale potential and the multiscale potential. So this is the slow component of the multiscale potential, and this is the multiscale potential, to be precise. And here we take small sigma to be equal to 0.5, and we can see that the effective potential, so this A scalar V prime, or just AV in this case, is given by as a very as much smaller slope with respect to slow scale of the multiscale potential, which means that if we just model our motion of our dynamics with a slow scale potential, then you have to take into account, let's say, the rugosity of the multiscale potential and have a much smaller slope for the potential. If you take sigma bigger, like for example, if you double it, sigma equals to 1, then we can see that the effective potential is closer to the slow scale component of the multiscale one. And then if we take sigma equals to 2, then you can say, well, they're almost indistinguishable. So here we have in red, so the model, the multiscale model. We have in green the single scale model, the effective model. And so our goal will be, when we are given observations coming from the multiscale model, let's try to fit a slow scale model of this kind. So in particular, in this talk, I will not discuss the diffusion coefficient. I will focus on the drift coefficient. And in particular, we will be so interested in estimating the coefficient capital A given observations from the multiscale model. So what do we know? We assume that we know the slow scale potential. So we assume we know the function V, actually just the function V prime. So we don't need to know the, let's say, the additive constant. We are not interested in it. And we ignore just the rest. So we don't know the functional form of this, the fast scale potential. We just know that it's L periodic from some period L. We don't know the diffusion coefficient. And of course, we don't know the Brownian realization that led to data. So what's the traditional way to fit this model to data? You can actually compute the likelihood function using Girsonov theorem. And you can actually compute the likelihood function and say that it's the exponential, the negative exponential through with some multiplicative constant of this function I here, which is made of a Ito integral of A scalar V prime plus 1/2 the deterministic integral of the square of A scalar V prime. So actually, we are given a likelihood function, and therefore it seems extremely reasonable to compute the maximum of let's say the argmax of the likelihood function and use this as an estimator. So that's what we're going to do. So we have the function I. Since the likelihood is the negative exponential of I, we have that our estimator is actually the argmin of I. And so actually one can easily compute that A hat is given by this metric, so the outer product of V prime with itself integrated in dt. And so the linear system, which has this as a matrix, and this is the right-hand side, where this is just the Ito integral with respect to the diffusion process itself of V prime v prime of xt epsilon. In dimension 1, which is actually maybe talks more to everyone, we have that the estimator is given by the ratio between the integral, the Ito integral with respect to the diffusion process of v prime over the deterministic integral of v prime squared. So we have, let's go back to the case for the generic n. We have that this estimator is given by this formula, so it's the solution of this linear system. And the theory of homogenization guarantees that xt epsilon converges to xt for epsilon going to 0. So we have this estimator, which is derived from this model. We have the solution of xt epsilon going towards xt. So one would reasonably expect that asymptotically, at least, so in the limit for infinite information, infinite data, and for epsilon going to 0, so where we are close to when we agree, let's say, with the theory of homogenization, then one would expect that the limit of our estimator is equal to A. Unfortunately, this is wrong, and one can show that actually what one finds when doing this asymptotic limit is not A, but alpha. So it's a drift coefficient of the slow component in the multiscale model. So as we have seen before, if the diffusion coefficient of the multiscale model is small, then we have a big difference between the slow component of the multiscale potential and the effective potential. So we are dependingly on the diffusion coefficient. This result tells that if we do nothing and we just compute this estimator, we may be arbitrarily wrong, and our effective model may not be an effective model at all. So let's go through a little bit of literature on what were the proposals to solve this issue. So as I said at the beginning of my talk, one popular solution is to subsample the data. So the theory for this is first being developed in a paper by Greg Pavliotis and Andrew Stewart, and then by other people later on. And in practice, this method has been applied in a series of several papers. For example, for oceanography by Kotter and Pavliotis, or in econometrics by Ait Sahalia and Giacomo. Then there are some works that estimate the drift coefficient using some martingale property of the diffusion processes, and the theory has been developed mostly by Sebastian Krumscheid with Greg Pavliotis and Kaliadasis. So there are some theoretical papers, and there's as well a very good practical paper where Sebastian and his co-authors employ their methods to estimate the effective model for applications in marine biology and, if I'm not mistaken, atmospheric sciences. Another series of works in another series of works, the estimator for the diffusion process is based on the eigenpairs of the generators of the generator of the diffusion process. And there are some works in the single scale. So let's say this estimators based on the eigendecomposition of the generator in the single scale case. And there is a work by Kessler and Sorensen, and another one by Comlin and Van den Einden. And actually the same authors propose the method that works as well in the multiscale case. There are as well some work in for the non-parametric case, which is achieved by Bayesian regularization. And these have been mostly in the single scale case, and they've been developed by Ivo Pokern, Andrew Stewart, and collaborators. So let's just see quickly how subsampling work. This is the estimator in the scalar case. So when the number of parameters we are trying to infer is equal to 1. And as we've seen before, the problem is that asymptotically, this estimator doesn't converge to capital A, so the effective drift coefficient, but to the drift coefficient of the slow component of the multiscale potential. So the solution is to compute a subsampled process. So we just take a a discrete process, which is the sampling of the continuous process with some step delta. And then you compute an approximation of the estimator with some Euler-Mariuama kind approximation for the integrals. So you can see at the numerator, we are just doing an Euler-Mariuama approximation. And at the denominator, we are doing just the left rectangle rule to approximate this integral. And therefore, the theoretical results for subsampling is a result of unbiasedness. So we have that if the subsampling rate is given by epsilon to exponent zeta, where zeta lays between 0 and 1, and if the final time, capital N, so we have that capital N delta is equal to T. So if the final time grows inversely proportional with respect to the scale separation parameter, then we have that in probability, the limit for epsilon to 0. So this limit for epsilon to 0, of course, since we have this assumption on time, is a simultaneous limit for epsilon to 0 and T to infinity. We have that the estimator tends to the effective drift coefficient. So as you see here, the range of the acceptable range for the subsampling rate depends on the scale separation parameter. So the scale separation parameter is something that you need to know in order to apply this method. Then the second issue is how do we choose the exponent zeta in 0, 1? And as I said before, the third issue is that we throw a lot of data in the garbage. For example, here I've just taken some numbers. So we have that if the scale separation parameter is 0, 1, if data is obtained at this frequency 10 to the minus 2, and if we set delta in the mid-range of this acceptable range, so square root of epsilon, then the 97% of the data is garbage. And actually, this effect is more acute if this delta tilde, so the data arrives with a frequency which is higher, or if the scale separation parameter is smaller, and in some application, this would lead to throwing even 99.5% of the data. So let's see.
Can I ask a question?
Yeah, please.
Yeah, going back to this this dropping of the data, is it possible to just compute different estimators, each of them
like
doing the separation of the samples and then averaging at the end? So at the end you end up using most of the data and don't throw almost anything.
Exactly. So one would think a good idea. It's actually a good idea. We tried it in practice and it works, but not much better than taking just one series of subsample data. It works better, but not much better. It's still dependent on the subsampling rate. And so the basic idea is just you take a subsample sequence that starts from, let's say, t equals to 0. Then you take a subsample sequence from t equal 1, where 1 is the subsampling, is the frequency at which you have data, and so far so forth. And you obtain a lot of estimators, you average them, and then you obtain an estimator, a global estimator. This works. Of course, it's more robust than just taking one sequence, but it's still very dependent on the subsampling rate. Thanks for the question, though.
Okay, thank you.
So let's see. So this is, to be clear, this is just taking one sequence of subsample data, the plots that I'm showing here. So we take just v of x to be x squared over 2, so that the effective model is an Ornstein-Uhlenbeck process. And we take subsampling and we vary this zeta exponent in delta equals epsilon to zeta. We take the final time to be fixed but big and the sinusoidal fast scale potential. And what we obtain, we can see that we take 3 different values for the diffusion coefficient, and we can see that the results are good. They're still a good approximation of the effective drift coefficient, which is this horizontal line, horizontal dashed line. But we have already that for 3 different values of the diffusion coefficient, the estimator seems to perform better in one case if you take zeta 0, so delta 1. Here somewhere in the middle, so delta to be square root of epsilon. And here somewhere at the right end of the spectrum, so somewhere around delta being just epsilon. So depending on the diffusion parameter, that is something we may not know, we have 3 different optimal values for our drift estimation. Of course, these lines should all flatten out if you take the limit for t to infinity and epsilon to 0. But yes, in general, you don't have epsilon going to 0, and you don't have an infinite amount of data. So what was our idea? So since when you subsample, since you're actually jumping from one local minimum to the other of this multiscale potential, and you're taking just a subset of the data, if you just connect the dots of the subsample path, let's say, you obtain a smoother path with respect to the original one, since you're eliminating the fluctuations that happen in close to each local minimum. So subsampling is kind of a smoothing process. So we thought, why don't we just directly smoothen the data out? So we introduced this new process, ZT of epsilon, which is given by the truncated convolution of the original data, xs epsilon, with some exponential kernel that is given here. So the kernel depends on 2 parameters, delta and beta, both positive. And we have that is given by delta to the -1 over beta times the exponential of r to the beta over delta. And c of beta is given by this value, and it's actually just a normalizing constant that makes this integrate to 1 if you integrate this thing from 0 to infinity. So there are still 2 parameters, but actually in the theoretical investigation, we fix the beta to 1. And if you fix beta to 1, what you obtain is a much simpler kernel. So you just have 1 over delta e exponential of -r over delta. So it's an exponential kernel. So what we can write in this case is that the differential, if you differentiate z of zt epsilon over dt, what you obtain by Leibniz rule is that this is equal to k0 xt epsilon plus the integral of k prime t minus s xs of epsilon. And since it is due to this exponential form, what you find is that this zt epsilon is equal to 1 over delta xt epsilon minus zt epsilon in dt. So we have that the Z process is actually the solution to an ODE, which is driven by the data. So if you take xt epsilon and zt epsilon together, they actually solve a system of 2 SDEs where the noise in the second component is degenerate. You have a noise in the first Brownian noise in the first component, and you don't have noise in the second one. So this allows us to do a theoretical analysis about that, because at our knowledge, if you take beta bigger than 1, then the process zt epsilon has memory, so it's not a Markov process anymore, at least as we understand it, and therefore you're not able to write this down, and you're not able to work with the usual tool of Ito calculus. Let's see graphically what happens when you filter the data. Is pretty clear. So you have in gray a trajectory coming from the multiscale process given by Vx x squared over 2, the usual sinusoidal fast scale potential, and epsilon 0, 1. So we see that the multiscale process jumps from one local minimum to the other and oscillates around this minima. And we have this black line, which is the filtered process, zt epsilon. So we can see that delta serves as a filtering width, and actually the bigger you choose delta, the smoother is z epsilon. The smaller you choose the delta, the more similar to x, let's say, is z of epsilon. So here we take delta to be equal to 1. Here we take delta to be square root of epsilon. So we can see that the process is already more similar to the original one. And here we take delta to be epsilon. So we can see that, yes, it oscillates still around the local minima, but in a much less wild, let's say, way than the original process. So just some quick properties of the filtered process. We have that if you take x epsilon and z epsilon as a couple, then the couple is geometrically ergodic, and it admits a smooth invariant density. So this is given by an application of Ormander's theorem. So again, on ergodicity, we have that the invariant measure mu epsilon has a density rho epsilon, which satisfies some Fokker-Planck equation, some stationary Fokker-Planck equation, where you can see here the multiscale potential, you can see here the diffusion term, and this term here, this additional term here is given by the filtering. Then you have that if you take delta to be independent of epsilon, so we have that delta is equal to 1, let's say, then we have that this measure mu epsilon converges weakly to some measure mu 0, whose density rho 0 is the solution to this single scale Fokker-Planck equation, where we have the filtering term, here we have the effective potential, and here we have the effective diffusion term. So let's go back to parameter estimation, which is actually the topic of this talk. So we had before the wrong estimator A hat, let's say that wrong, the one that converges to the wrong result, A hat x epsilon t, which is given by the solution of this linear system. So this matrix -1 times this right-hand side. And our idea was to replace the original process xt epsilon with its filtered version zt epsilon, but not everywhere. And first we replace it once in this matrix. So you take the outer product between v prime z and v prime x, and in the argument of the right-hand side. So we are still integrating with respect to xt epsilon, but we're integrating v prime of zt epsilon. Let us remark that A hat x epsilon t is well defined if this matrix is not non-singular. We assumed it in our work, but we are actually pretty certain that this holds almost surely, since in any case, this is a random matrix, and it's the sum, let's say the infinite sum of rank 1 matrices, and which are random. And so we kind of think that the determinant of this matrix is 0 with probability 0. And therefore that the matrix is almost surely invertible, but we were not neither too interested nor able to prove it. So we just assume that the matrix is invertible. So recall that we have this filter process. The delta parameter is the width of the smoothing window. And recall that we have the estimator, which is given by, let's say, this mixed between the filter process and the original process. Then we can prove that if you take the filtering width to be equal to epsilon to the power of zeta, where zeta is serves the same role as in the subsampling case, then we have that in case zeta is equal to 0, so in case delta is equal to 1, or let's say independent, it doesn't go to 0 with epsilon, then we have that the limit asymptotically in time and in epsilon of the estimator is equal to A almost surely. So this is a big improvement with respect to subsampling, because already we don't have improbability anymore, but we have almost surely. And then you have zeta equals to 0, which says that we don't need to know the scale separation parameter in order to obtain an unbiased estimation of the effective drift coefficient. Then if we take the exponent zeta to be between 0 and 2, then we have that the estimator converges as well to A, but just in probability. And finally, if you take zeta bigger than 2, so let's say you're filtering too little, because if zeta is bigger than 2, it means that the filtering width is very small. So for example, epsilon to the power of 3, which means that you're basically not filtering the data, which means that here you put x more or less, here you put x more or less, and therefore you go back to the previous estimator, and therefore you converge to alpha, which is the drift coefficient of the slow scale component of the multiscale potential, which is something we don't want. What is interesting though is that here the upper bound for zeta is 2, and here the lower bound to get wrong result is 2 as well. So we have kind of a sharp transition, as at least asymptotically, we have a sharp transition at the point zeta equals to 2, or delta equals epsilon squared. So let's see this numerically through a numerical example. We take our favorite process, the Ornstein-Uhlenbeck potential, And we use the filtering with beta equals to 1, which is the one we developed the theory for, and delta equals epsilon to the zeta, with zeta between 0 and 3. So between 0 and 2, we should be in the range of validity of our theorem. Over 2, we should not. So we can see here that our estimator for delta between epsilon and epsilon, between 1 and epsilon is very close to the effective potential coefficient, drift coefficient. And then it transitions to the value of the drift coefficient in front of the slow component of the multiscale potential when you take delta to be smaller than epsilon squared. So this transition may happen, may look like it's happening at a slow pace. So here we have lots of values for which even if we're in the validity range, it's not really close to the effective drift coefficient. But let's remark that the x-axis is rescaled with respect to epsilon, and that this is logarithmic. So actually, this is extremely fast. So in the previous plot, we were fixing the final time and taking 3 successively smaller value of epsilon. And here we take a fixed value of epsilon, and we take 3 successively bigger values for the final time. And we can see that for the biggest final time, the estimator is closer to alpha for, so the wrong one, if we take delta too small, and it's closer to A if delta is in the range of validity of our theorem. So we had these results already before. I've shown these results for the subsampling, always in the Ornstein-Uhlenbeck case. And I've shown before that the results are extremely dependent of the subsampling rate. So let's see if we take the same values for delta as we took for the subsampling rate in our filtering framework. What happens? We have that actually the results are much better. So let's focus one value of sigma at a time. We have that for the smaller value of sigma, the subsampling results and the filtering results are not much different. But then if we take the rightmost value, so for sigma equals to 1, then we have at least for this zeta equals to 0, so for the subsampling parameter equals to 1 or the filtering width equals to 1, here we're getting quite wrong results, whereas here we are getting extremely correct results. So in general, we have that in each case, the best result is obtained when we fix the filtering width to be equal to 1. And in general, even if we take a filtering width which is smaller and which vanishes with respect to epsilon, then we have that the results are quite good. So I was mentioning at the beginning that the filtering can be done with this beta parameter. So we had a whole class of filters that depends on this parameter beta. I've shown the theory for beta equals to 1, since for bigger values of beta, we haven't developed the theory yet. But still, we did some numerical experiments for higher values of beta. And in particular, here we take beta equals to 5. And we can see that the results, still taking the filtering width to be equal to epsilon to the zeta, we have the results are extremely good. So we have practically a flat curve for the 3 values of sigma, extremely close to the effective drift coefficient. So another experiment is done by taking a variable sigma. So instead of the 3 pictures we had before, we take maybe 20 values of sigma ranging between 0, 1, and 2. We see here the dashed curve is the value of the effective drift coefficient in this case. And the 3 figures correspond to the filtering width or the subsampling rate to be equal to 1, square root of epsilon, and epsilon. We can see that the subsampling kind of follows the curve for some values of sigma, but then gets lost. And this happens to different extents, but still always in the 3 cases for the 3 subsampling rates. And here as well, the subsampling doesn't give good results for small values of sigma. But we can see that the curves corresponding to filtering are extremely good, and they follow the drift coefficient of the effective drift coefficient in all scenarios, except here where the filtering with beta equals to 1 kind of follows the subsampling curve at the beginning, but then aligns to the effective drift coefficient with a small margin of error, but still I insist that the best implementation of our filtering method is obtained when you take delta equals to 1. And in this case, you can see that the filtering works extremely good. So I don't have to mention it, but I mention it nevertheless. For beta equals to 5, in all 3 scenarios, the curve is extremely close to the value of the effective coefficient. So let's see just numerically what happens varying this coefficient beta. So we fix everything else and we vary the coefficient beta. And you can see here for 3 different values of the diffusion coefficient that actually the results stabilize quite fast with respect to beta. So we have, before we were taking beta equals to 5, just to be sure somehow, but actually we can see that already with beta equals to 3 or 4, the results are extremely good with respect to a single application like beta equals to 1. I've solved this method using a multidimensional coefficient. So far, I've explained and showed experiments with only 1 coefficient. So let's do an experiment with multiple coefficients. So we take the potential to be equal to the sum of 4 Chebyshev polynomials of the 4th kind. So as you may know, the Chebyshev polynomial of the 1st kind are given by this recurrence relation. So we have 1, x, and then we have just this recurrence relation for 3 onwards. We want to estimate the drift coefficient when the slow scale potential is given by a sum of the first 4 Chebyshev polynomials multiplied by some coefficient. And we take the filter to be implemented just with delta equals to 1, beta equals to 1. And for the subsampling, we just choose delta equals epsilon to the 2/3, since in the original paper by Greg Pavliotis and Andrew Stewart, the exponent 2/3 is said to be the optimal one, heuristically. So we see that if we do no preprocessing, we actually converge. We are very close to alpha scalar V prime. Sorry, here it should be V, not V prime. It's just alpha scalar V. So this is the potential, not its derivative. We have a bistable potential. And we have that if we do nothing, then our estimator of the effective potential is actually estimating the slow scale component of the multiscale potential. If we do subsampling, then maybe this rate wasn't the best one, but still it was said to be the optimal one. But what we find is nowhere close to anything. And if we do filtering, our method implemented with, let's say, naive parameters, so just take everything to be 1, we have that the result is extremely close to the effective potential. So let's see, we had so the original coefficients we used for generating the data were -1, -1/2, 1/2, and 1. We have that the theoretical values for the effective drift coefficients are given by these values here. And you can see here, if we do nothing, we are close to the alpha coefficient. If we filter the data, then we are close to the A coefficient, extremely good for, extremely well. And if we do subsampling, then we kind of capture the coefficient number 1, but then we get lost for coefficients 2, 3, and 4. So I'm now done with the pointwise estimation of the drift coefficient. And I was saying at the beginning that we would like our method to be applicable to the Bayesian framework. So in the Bayesian framework, what we need is a likelihood function, a prior function, and then you would compute the posterior function as, let's say, a multiplication of prior and likelihood. So the likelihood is something we have because we were computing this maximum likelihood estimator, and by Girsanov theorem, then we have that the likelihood is this negative exponential of this I function, as I showed you at the beginning. Then we just introduce a notation. We call M to be this matrix. So 1/2 square root of T, sigma, capital sigma T. This is the effective diffusion coefficient of this outer product of V prime with itself. And H, the same normalization constant times the Ito integral of V prime of X. Then we have that since if we assume M to be not just semi-positive definite, but definite positive definite, then we have that, that this is in any case, but we have that the log likelihood is given by minus H transpose A plus the quadratic form ATMA over 2. And therefore that the log likelihood is a quadratic function of A, which makes it a Gaussian likelihood. So we have that the log likelihood is a quadratic function of A given by this formula. M we assume to be a positive definite matrix, that our so let's say we compute the Radon-Nikodym derivative as to be the likelihood function normalized, the normalized likelihood function. Then you have that the posterior is Gaussian. So in terms of densities, if you take a Gaussian likelihood, the negative exponential of the quadratic function, and you multiply it by another negative exponential of the quadratic function, then you obtain a Gaussian density with normalism, of course. And so the posterior is Gaussian, and what is left to do is just to compute its mean and covariance in order to have a full characterization of the posterior. So this can be quickly done by completing the squares, and we can find that the posterior measure, which of course depends on the final time, so the horizon of the data we are given, and on the multiscale parameter, is given by a Gaussian of average MT and of covariance matrix CT, where the inverse of the covariance, so the precision matrix, is given by this formula, C0 minus 1 plus Tm, where we can see that actually the prior precision matters less and less when we are acquiring more and more data, so if T becomes bigger and bigger. And then we have that the mean is given by the solution by actually you just multiply this expression by the covariance matrix, and you find the mean. So we recall M to be, so we just introduced them, but we recall M here is given by this expression, and H here is given by this expression. So we have that, actually, as I said before, the precision matrix tends to 0, and actually one can see that M of T tends to be equal to CT times H, which actually makes that the posterior measure, as one may expect, when we increase the amount of data that we're given, the precision increases, so the covariance shrinks to 0, and at the same time, the posterior measure shrinks towards the MLE. So it shrinks toward, let's say, a Dirac measure concentrated on the maximum likelihood. And but we have that, as we have shown in the beginning, we have that the maximum likelihood estimator of the drift coefficient doesn't go to the effective drift coefficient, but it goes to the multiplier of the slow scale potential within the slow component of the multiscale potential. So we have this negative result, is that if you take the posterior measure of the complement of any ball for any given radius, small, arbitrarily small ball. So if you take the complement of this ball and you take the posterior measure with the and the ball is centered in the multiplier of the slow component of the multiscale diffusion, then we have that asymptotically, this expectation is taken with respect to the Brownian motion. This asymptotically, we have that this measure is given by 0. So in formulae, this says what I've explained before, so that the posterior measure shrinks to the MLE, and at the same time, simultaneously, the MLE goes towards the wrong value. So our posterior concentrates towards the wrong value. So can we use our filtering procedure to correct this faulty behavior? So let us recall that we had our filtering estimator, we had this substitution of X with Z, but not everywhere. So we had a Z here, a Z here. And actually, one can write more compactly the filtering estimator to be given by the solution of minus, so the solution of this linear system minus M tilde minus 1 H tilde. And this filtering estimator would be the MLE associated to this log likelihood. So we have minus H tilde T transpose A plus A transpose M tilde A over 2. But we have a problem. So M tilde is not symmetric, since you're taking v prime Z, v prime X, which could be solved easily by just taking the, actually this quadratic form is equal than the quadratic form you would have by taking just a symmetric part of M tilde. But what we don't have is that this matrix is not, for sure, is not positive definite. Actually, even in practice, we had that some eigenvalues were smaller than 0, and therefore this A hat K is not a minimizer of this log likelihood. But we had the matrix M before, so instead of Z, you have X here, which we assume to be positive definite. It's for sure semi-positive definite, and we assume to be positive definite. And we have that if you take this log likelihood, so we have minus H tilde transpose A, AT M A over 2. Then we have that it's Emily, since M is symmetric positive definite, is indeed given by minus M minus 1 H tilde. And we called this value A hat A tilde of K. So A tilde filtering, let's say, of the data final time. So we have that, we have another estimator, another maximum likelihood estimator, which is given by this quantity. And it's actually slightly different than the one before. So before we were modifying both the matrix and the right-hand side. Here we're just modifying the right-hand side. What we lose by doing this is that we don't have this very nice property that if we take delta equals to 1, then we have almost sure convergence. Actually, we don't have convergence in this case. But if we take delta to be epsilon to the power zeta with a positive exponent zeta smaller than 2, so the range of validity of our previous estimator, but not in 0, then we have that the asymptotic limit of this new estimator is given by A. So we introduced it just now because in the Bayesian framework, it's very nice because it's a minimizer of some likelihood function, but still it works it doesn't work as good as the filtering estimator where you modify both the matrix and the right-hand side. So here we have another quadratic function as the log likelihood. So if we, again we take a Gaussian prior, then we obtain again a Gaussian posterior, so we can fully determine the posterior measure, but just determining its mean and its covariance matrix. And in particular, we have that the precision matrix is the same as before. Since we have the same matrix M here as before, we have that the precision matrix is given by the same thing, but the mean is modified. So here we would have had before H, and here we have the M tilde T is actually given by the same expression as before, but instead of H, we have H tilde. So the posterior is given by this expression, and you can already see from 5 minutes, I'm almost done. Thanks, Sebastian. So the precision matrix is given by this. The mean is given by this expression, this implicit expression, and we recall M to be given by this matrix here, and H tilde to be given by this vector here. And then we have a positive result, which is that if we take the same, so we had before that if you took the posterior measure, it would shrink towards the MLE, and the MLE would go towards the wrong value. Here we have the same effect since the precision matrix is the same, so the posterior measure shrinks at the same rate as before. And we have that if you take, but it shrinks towards the MLE, but this time, due to the theoretical result of the filtering estimator, we have that it shrinks towards the good value. So this is summarized by this theorem here. So we have that for any ball, so any radius C arbitrarily small, and if you take delta to be equal to epsilon to zeta, and I stress out here, this is not the best because we still have to know the scale separation parameter, but this is the only way to make it work in the Bayesian framework. So if you take this positive radius for any positive radius, the measure, the expected measure of any ball, the complement of any ball centered into the effective drift coefficient tends to 0. Therefore, this says more, quantifies better what I've been saying before, so that our posterior measure shrinks towards the MLE, and the MLE simultaneously goes to the effective drift coefficient. Let's see this in a last numerical example. So we have we take a bistable potential. So we take V1, two components potential, where we have V1 to be given by x, the fourth power of x, and V2 to be a negative quadratic potential. And we take alpha 1, alpha 2 to be equal 1 and 2, so that the homogenized coefficient here is the cross, so it's around 0.0408. And we take the filtering with beta equals to 1 and delta equals to epsilon. So we took the midpoint of our range of validity, which was epsilon from 1 excluded to epsilon square excluded. So more the other way around, from epsilon squared to 1. And then we see that the posterior measure, whose isolines are depicted in this picture, you can see that it shrinks towards the MLE. And the MLE here at t equals 100, we were a bit far away from the homogenized coefficient, drift coefficient, but then the MLE moves towards the drift coefficient, and at the same time, the posterior measure shrinks towards the MLE. And so we have, on the one hand, we have that the mean of our posterior is very close to the true value of the diffusion coefficient. And on the other hand, we have that increasing time, we have a shrinkage of the posterior measure, which denotes more and more certainty on our inference procedure. So just to conclude, to wrap everything up, at the beginning of my presentation, I gave some desiderata for our new method, which was to be consistent with respect to homogenization theory, to be robust versus subsampling techniques, so more robust in its parameters, to be applicable as a black box tool, which we achieved, since at least in the maximum likelihood estimation part, we don't need to know the scale separation parameter to obtain consistent result with respect to homogenization theory. And then we have that just by modifying a bit our estimator and by working out the math a bit, we have that our method is amenable to a Bayesian framework. So what's left to do is to combine this filtering data with other techniques. So for example, the ones developed by Sebastian, I don't know if that would be possible, or the spectral decomposition of the spectral techniques for estimating the drift coefficient. Another one would be to study theoretically what happens if you take a beta bigger than 1, which appears to be extremely good. So let's see, is it possible to study that theoretically as well? And then, like, it would be nice to apply this filtered data technique to other kind of multiscale SDEs, not just a simple one with an additive noise, but maybe with a more complicated multiplicative structure of the noise. So that's all for me. Thank you very much for your attention.